In this lecture, you'll learn about MetroCluster, which provides high availability with your storage system spread across two separate physical buildings. Before we get into how MetroCluster works, it's going to make things easier to understand if we review how ONTAP traditional high availability works first. So with normal high availability, all of the nodes in your cluster are going to be configured as high availability pairs. So each node in a high availability pair serves as an HA peer for each other. And you can see here we've got controller 1 and controller 2. Aggregate 1 is owned by controller 1 and aggregate 2 is owned by controller 2. And you can see that both controllers are connected to their own disk shelves and also to the disk shelves of their HA partner. So with traditional high availability, if controller 1 fails, then controller 2 is going to realize that because it's going to stop getting keep alives across the HA connection. And the other way that it can realize it is that the service processor in controller 1 can signal over to controller 2 to let it know that controller 1 has had a failure and that controller 2 needs to take ownership of its disks. So when that happens, controller 2 will take ownership of controller 1's disks, and now both aggregate 1 and aggregate 2 are owned by and are being served by controller 2. When controller 1 comes back online again, controller 2 will give ownership of aggregate 1 back to controller 1. So you can see there that high availability helps if we have a controller failure. But what if the entire building goes down? So looking at that, now it's not just the controller, but it's the entire building of building 1 that is failed. So controller 1 and its disk shelves are in building 1, controller 2 and its disk shelves are in building 2. And when the building goes down, obviously it's not just the controller, it's the disk shelves are going to be down as well. So now in this case, controller 2 would realize that controller 1 has gone down because it's not going to be receiving keep alives from controller 1. And controller 2 is connected to controller 1's disk shelves, but the problem is that the disk shelves have also gone down, so it doesn't help having controller 2 connected to them. The aggregate that is on those disk shelves is still not going to be available. So you can see here that traditional high availability, it gives us redundancy for controllers, but it doesn't give us redundancy for our disk shelves. So this is where MetroCluster comes in. MetroCluster does give us redundancy in case of entire building failing by combining high availability and sync mirror. So you saw there that traditional high availability gives you redundancy for your controllers. You learned earlier in this section that sync mirror gives you redundancy for your disk shelves. So by combining high availability and sync mirror, that gives us redundancy for the entire building. So with MetroCluster, sync mirror is used to mirror the aggregates to a disk shelf in each separate building. High availability provides the redundancy for the controllers, and sync mirror provides the redundancy for the disk shelves. MetroCluster supports an active-active configuration. Each separate physical site will serve data to its local clients, and it acts as a secondary to the other site. You can selectively choose which aggregates to mirror, because when you're using sync mirror, it requires double the amount of disks to be used. You can cut down on your disk hardware costs by only mirroring the mission-critical aggregates. Typically, though, in a MetroCluster configuration, you are going to have all of your aggregates being mirrored. MetroCluster uses synchronous replication. So data is written to both buildings before the acknowledgement is sent back to the client. Because it uses synchronous replication, that gives us an RPO of 0. If one building goes down, we know for sure that the second building has got the same state of the data completely up to date. No data is lost in the case of an outage. So looking now at when we have a building failure and we do have MetroCluster set up now. So you can see here now with MetroCluster that controller 1 owns aggregate 1. So aggregate 1 plex 0 is in building 1 with controller 1. But with sync mirror, we've got aggregate 1 plex 1 is in the other building with controller 2. We want this to be an active-active configuration, so aggregate 2 is owned by controller 2. So aggregate 2 plex 0 is in building 2 with controller 2. That is mirrored over to aggregate 2 plex 1, which is in building 1, connected to controller 1. Now, if we have a building failure, so here building 1 fails, well, we've still got a controller working, and we've still got a copy of the data in aggregate 1 and a copy of the data in aggregate 2, so the data is still going to be accessible to our clients. For the failover to building 2 when building 1 fails, you can either do that manually or you can have an automatic switchover to site 2. Well, as well as the data being mirrored between the two sites, the ONTAP configuration is mirrored between the two sites as well. So if you do make a change to the ONTAP configuration, MetroCluster does act as a single system. So whenever you make any changes, that is going to be known to both sites. MetroCluster can be provisioned with 2, 4, or 8 nodes in the system. So looking at 4-node MetroCluster first. Here, the 2 nodes in each site are an HA pair for each other. So if we've got controller 1 and controller 2 in site 1, they're an HA pair for each other. Controller 3 and controller 4 in site 2, they're an HA pair for each other as well. Sync mirror will mirror the aggregates across both sites, and it's an active-active configuration. Each site serves read data to local clients from the local plex, and also one site is going to be the write copy for each aggregate. If a controller fails, the other controller in the same site will take over. So if it's just a single controller that fails rather than the entire building, it's the controller in the same site that will take over for it because it is that node's HA partner. If a site fails, the owner of the other plex in the other site will take over for that data. So looking here at 4-node MetroCluster, we can see in building 1, we've got controller 1 and controller 2. They are an HA pair for each other. And in building 2, we've got controller 3 and controller 4. They are an HA pair for each other. Aggregate 1 plex 0 is owned by controller 1. We've got aggregate 1 plex 1 is over in building 2 with controller 3. Aggregate 2 plex 0 is owned by controller 2, and it's mirrored over to aggregate 2 plex 1 connected to controller 4. Aggregate 3 plex 0 is on controller 3, mirrored over to controller 1, aggregate 3 plex 1, and aggregate 4 plex 0 owned by controller 4, mirrored over to aggregate 4 plex 1 over in the other site. So you can see that it is an active-active configuration because aggregate 1 and aggregate 2 are owned by the nodes over in building 1. Aggregate 3 and aggregate 4 are owned by the nodes in controller 2. Each aggregate is mirrored to both sites. Another way that we could diagram this is you can see that controller 1 and controller 2 in building 1 are an HA pair for each other. Controller 3 and controller 4 are an HA pair for each other, and the aggregates owned by controller 1 are mirrored over to controller 3 in the other building. The aggregates owned by controller 3 are mirrored over to controller 1 in the other building. The aggregates owned by controller 2 are mirrored over to controller 4, and the aggregates owned by controller 4 are mirrored over to controller 2. So looking at what happens if we have a failure, if controller 1 fails, just a single controller, that is going to fail over to controller 2. Controller 2 will temporarily take ownership of aggregate 1 in addition to its own aggregate of aggregate 2. Okay, so that's if a single controller fails. If the entire building goes down, then building 2 will take over, and you can see that we've got a copy of aggregates 1, 2, 3, and 4 in building 2. Okay, so that was 4-node MetroCluster. We can also have an 8-node MetroCluster configuration as well. With an 8-node MetroCluster configuration, it works the same way. We just double up on the amount of hardware. So you saw that when we had 4-node MetroCluster, it was this configuration at the top here. Well, with 8-node MetroCluster, we're going to have the same configuration for our first 4 nodes, and that's going to be our DR, Disaster Recovery Group 1. And then we do the same thing with the other 4 nodes. They're configured the same way, and that is our DR Group 2. Okay, so let's look at a possible hardware problem that we would have with this. And that is that in a normal HA pair, the controllers have an HA connection for NVRAM mirroring, and they are connected to each other's disk shelves with SAS cables. And the problem is that traditional SAS cables only support very short distances, just a few meters. So that's fine if your controllers are in racks, which are next to each other in the same building, but if they're in different buildings, then they're going to be more than a few meters apart. So how are the controllers going to be connected to each other's disk shelves? And the way that we solve the problem is with Fibre Channel, because Fibre Channel supports long distance cables, and it can be used for the NVRAM mirroring and disk shelf connections for MetroCluster. A pair of Fibre Channel switches are installed in both sites when we use Fabric attached MetroCluster. There are some other options that I'll get to coming up after this. Here we're talking about Fabric attached MetroCluster. When you use that, it's got a pair of Fibre Channel switches in both sites. We still have a problem though. So the Fibre Channel is going to allow us to have connections between the two sites, but the current models of disk shelves have SAS ports in the back. They don't have Fibre Channel ports, so how are we going to connect to them with Fibre Channel? Well, we add another piece of equipment to solve that problem. That is the ATO Fibre Bridge. It is a Fibre Channel to SAS gateway. The controller connects to the Fibre Bridge with Fibre Channel cables via the Fibre Channel switch, and then the Fibre Bridge connects the disk to the disk shelves with SAS cables. So let's see how that works. So now we're looking at a diagram of 4-node Fabric attached MetroCluster configuration. So you can see here we've got Site 1 Controller 1 and Site 1 Controller 2. In Site 1, they are connected to 2 Fibre Channel switches in Site 1. We put in 2 switches for redundancy. Over in Site 2, we've got Site 2 Controller 1 and Site 2 Controller 2, and they're connected to 2 Fibre Channel switches in Site 2. Then the Fibre Channel switches are connected with Fibre Channel down to the Fibre Bridge. So you see here that the connection from the controller to the Fibre Channel switches is of course Fibre Channel. The connection from the Fibre Channel switches to the Fibre Bridge is also Fibre Channel as well. Then the connection from the Fibre Bridge to the disk shelves is SAS. Because it's SAS ports on the back of the disk shelves, we need to use SAS cables here to connect to them. So what the Fibre Bridge is it's a Fibre Channel to SAS gateway. So we have that in building 1. We have the same thing in building 2 as well. So now for the controllers to connect to the disk shelves, for the disk reads and writes, that's connected via Fibre Channel switches and then down to the AO Fibre Bridge, and that gives us connectivity both within the site and across the 2 sites as well. The maximum distance for Fabric attached MetroCluster is 300 kilometers if you're using native Fibre Channel, 200 kilometers if you're using FCIP. So the cabling in that previous diagram showed the node initiator connections from the controllers to the disk shelves in both sites for reads and for writing to disk during consistency points. That is traditionally the job of the SAS cables, but as we said, SAS cables aren't long enough to do that across 2 different buildings, so that's why we had those node initiator connections with MetroCluster using Fibre Channel, and that is used for the traffic going to and from the disk shelves. But with MetroCluster, writes still work in the same way as they always do in ONTAP, where they're written to NVRAM before being written to disk. And they need to be written to NVRAM in both controllers. So the NVRAM mirroring also takes place between the controllers in the different sites over the fiber channel network as well. That uses separate connections, so separate ports and cables than are used for the normal disk reads and writes. It uses separate FCVI for fiber channel virtual interface connections from the controllers. So looking back at the same diagram again, this is the diagram you saw earlier. These are the connections that are being used for the disk reads and writes. So from each controller, it has got two connections going down to the fiber channel disk shelves, again for redundancy. For the NVRAM mirroring, that uses separate ports and cabling. So on both controllers, we have two connections again for that, going down to the fiber channel switches. That allows us to do our NVRAM mirroring between the two sites. Okay, now let's look at the configuration replication service. So as well as the data in the volumes and the aggregates being mirrored between the two sites, we also need to have the ONTAP configuration known in both sites as well. So the ONTAP configuration, including SVM, length, volume, and LUN settings, is replicated between the two sites using the configuration replication service. This information in the configuration replication service does not use the fiber channel connections. The CRS replicates over a normal IP network using cluster peering and intercluster lifts. So for the NVRAM peering and the disk reads and writes, that uses the fiber channel network. For replicating the ONTAP settings, that uses the configuration replication service, and that runs over a separate IP network. Fabric attached MetroCluster that we just covered there is supported for all MetroCluster configurations. That's 2, 4, and 8 node configurations. For 2-node MetroCluster, there's a couple of other different configurations that are supported. So for 2-node MetroCluster, it supports Stretch MetroCluster and Stretch MetroCluster with SAS Bridges, in addition to Fabric MetroCluster. Looking at Stretch MetroCluster first. In 2-node Stretch MetroCluster, the controllers are cabled directly to the disk shelves with NetApp proprietary long-reach SAS cabling. So these special NetApp SAS cables, they can run for a longer distance than traditional SAS cables do. Fiber channel switches and the 8.0 fiber bridges are not required with this configuration. The maximum distance is 100 meters. So it is still quite a short distance between the two sites, but if this is within the same campus, you've got a couple of buildings within 100 meters with each other, and you're using a 2-node configuration, then Stretch MetroCluster is a viable solution. So looking at how this works, between controller 1 and controller 2, because they're within 100 meters of each other, we don't require fiber channel to connect to the controllers to each other's disk shelves. We can use the special NetApp proprietary SAS cables. They will run up to 100 meters long. We still do have a fiber channel connection between the controllers for the NVRAM mirroring. That uses FCVI interfaces on the controllers, a fiber channel cable. We have them connected directly to each other, so there's no need for a fiber channel switch. And because the controllers are connected directly to each other's disk shelves, there's no need for the fiber bridge. Next up, we can have Stretch MetroCluster with SAS Bridges. So in 2-node Stretch MetroCluster with SAS Bridges, the controllers are cabled to the disk shelves via 8.0 fiber bridges. So this does use the fiber bridge. The controller to fiber bridge connection uses fiber channel as usual. Fiber channel switches are still not required here. The maximum distance is 500 meters. So this is still going to be within the same campus, but we can go a bit further because we're using fiber channel connections to the fiber bridges. So looking at the configuration here, rather than using SAS cables to connect the controllers to the disk shelves, the controllers are connected to fiber bridges using fiber channel connections. We also have that fiber channel connection directly between the controllers again for the NVRAM mirroring. And in 2-node Fabric MetroCluster, the system is cabled the same way as for 4-node Fabric MetroCluster as you saw earlier. So this is the third of the 3 available options for 2 nodes. So you see with 2-node Fabric MetroCluster, it looks exactly the same as the 4-node did, but we've just got 1 node in each site rather than 2 nodes in both sites. Okay, another thing we can do is MetroCluster over native IP. MCIP connects clusters over Ethernet rather than fiber channel switches. So the FCVI adapters and the 8.0 fiber bridges are not required. They are specific to fiber channel. So we still need to get the NVRAM mirroring and the connectivity to the disks for reads and writes to be available. For that, we've got iWarp over IP is used for the NVRAM replication, and iSCSI over IP is used for the disk connectivity across sites. So with MetroCluster over native IP, we don't need to use fiber channel. Everything runs over IP instead. This does support advanced disk partitioning on AFF systems, which is not supported when we're using the fiber channel configuration. But a limitation is that currently only 4-node MetroCluster is supported. The maximum distance when you use this configuration is up to 700 kilometers between the sites. So looking at MetroCluster over native IP, well, I don't need to give you any kind of complicated diagrams here because it's just running over your normal IP network. So whatever your normal IP connectivity is between the sites, MetroCluster is going to be running over that. So you can see here in the diagram, I've just got each controller connected up to an IP network. Okay, looking at the client connectivity now. Client identity is preserved during a switchover. If a site fails, clients connect to the same IP addresses or WWPNs they were using before on the other site. So if you do have a building failover, everything looks exactly the same as before to the clients. Obviously, this is a good thing because we want to have a very, very fast failover. We don't want to have any settings changing when we do that, and we don't need to. The client data must therefore span both sites, because the same IP addresses must work in both sites. So you're going to need to have the same layer 2 network available in both locations. So our site connectivity options that would provide that would be dark fiber or an MPLS layer 2 VPN service or a proprietary solution such as Cisco OTV, that's overlay transport virtualization, or a SAN fabric that spans both sites for fiber channel. If you're not sure how to configure this, speak to your networking team. They will know about these different options and they will be able to guide you on what the best solution is for your particular environment. Looking now at if we are wanting to switch over between the 2 different buildings. So there would be a switchover if one of these buildings goes down, but also maybe we want to do a planned switchover where we're going to do this manually. That is going to be useful for disaster recovery testing. Yes, once this is set up, you definitely do want to test this. You don't want the first time you need the failover to work when you really need it to work because a building has gone down. So you are going to test this. Other reasons to do a planned switchover would be for technology refreshes. If you're going to be upgrading the hardware in your cluster, then you can take one site down and upgrade the hardware there. And then once the hardware has been upgraded, you could fail back again. Other reasons would be for scheduled maintenance, if you need to take a building down for maintenance, and also for disaster avoidance. For example, if you've received a weather report that severe flooding is expected where one of your sites is, then it would be a good idea to do a planned switchover and then gracefully switch over to the other site, wait until the bad weather is over, and then you could switch back again. To actually do the switchover, you should verify the MetroCluster health before doing so. The command to do that is MetroCluster switchover simulate. The command to switch sites, you can do that with a single command, which is MetroCluster switchover. So very easy to do this when you do have to fail over. And to switch back, the commands for that are MetroCluster heel phase aggregates and MetroCluster heel phase root aggregates first, and then MetroCluster switch back to revert back. So very easy, very quick if you need to do a manual failover and failback. Looking now at if there's an unplanned switchover. So if something has actually gone wrong in one of the buildings and we've unexpectedly lost that building. Automatic switchover occurs if all nodes at a site fail due to node power off, node power loss, or node panic. In other cases, switchover occurs manually. You saw how to do that on the previous slide, or through the use of MetroCluster Tiebreaker software. And you did see on the previous slide that to do the switchover manually, it only takes a single command. So it's very, very quick to switch over when you do realize that you do have to do so. But the other way that you can do it is automatically with MetroCluster Tiebreaker software. We'll get to that in a minute. So with the unplanned switchover, the reason it works like that is to prevent a split brain scenario where both sites lose connectivity with each other and assume the primary role for all aggregates. Basically, we don't want a switchover occur just because we've lost network connectivity, but both sites are actually still up and functioning. That would lead to different data being written to the plexes for the same aggregate in both sites, so we would have inconsistent copies of the data. We really need to avoid that at all costs. So this is what could happen with a split brain, where we lose the network connectivity between the two sites, but both sites are still writable. If we do have a split brain like that, we want to make sure that we are not writing to both sides at the same time, in which case we would end up with different data in both sites. So we can do the manual switchover. When you do the manual switchover, you saw it's the same command again, MetroCluster switchover, but when only one site is available, you need to force it. So you add the option forced on disaster true. The other way that we can have switchover happening is with MetroCluster Tiebreaker. And what MetroCluster Tiebreaker does is it makes sure that it's not just a network outage between the two sites that makes them look like MetroCluster is down. With MetroCluster Tiebreaker, we have a third site monitoring the connectivity. So we have to lose connectivity going to two different locations rather than just one, making sure that it's not just a network outage. So MCTB, MetroCluster Tiebreaker, is a Linux application that runs in the third site with connectivity to both clusters. That network connectivity to both clusters should be on a separate path. You don't want to have a single point of failure for both paths on your networking, or you could have that split brain situation again. It's used to independently monitor both sites and send SNMP alerts if issues are detected. It can also be configured to automatically switch over in the case of a site failure. So you can have it configured where it's just going to give you a notification if it looks like things are down, or you can have it where when things are down, it will actually trigger a switchover automatically. Recovery time objective is 120 seconds for automatic switchover. The reason it's 120 seconds is that the MCTB software will run through some checks to make sure that the site is definitely down before it fails over to the other site. Let's look at what those checks are. So MCTB establishes SSH sessions with each node's management IP address. So this runs over an IP network. If the SSH session to a node goes down from MCTB, it checks the HA status within the site. So say we've got nodes 1 and 2 in one site, nodes 3 and 4 in the other site. If node 1 goes down, if MCTB, the SSH session to node 1 is not available, then it will check the HA status on node 2 in the same site. If it can't reach either node of an HA pair, so if node 1 and node 2 are both down, then they're going to be declared unreachable. So at this point, MCTB knows that it does not have connectivity to the nodes in site 1. Site 1 does appear to be down, but it's going to double check this. MCTB then asks the other site, so it asks site 2 via SSH, if it has connectivity over the FCIV connection or intercluster IP network. So you can see here that we've got those two separate network paths. For site 1 to be marked as actually definitely down, then MCTB needs to have lost connectivity to it over the IP network, and also site 2 needs to have lost connectivity to it over the Fibre channel network. If that is the case, we can be pretty sure that site 1 is definitely down. You can now at this point have MetroCluster Tiebreaker just send you a notification of that, or you can have MetroCluster Tiebreaker go ahead and initiate the failover to site 2. Okay, last thing to tell you about MetroCluster. MetroCluster can be used in conjunction with SnapMirror and SnapVault. They're not mutually exclusive with each other. So you could use MetroCluster to provide synchronous replication between two sites up to a distance of 700 kilometers, depending on the configuration you use. And you could also use SnapMirror to asynchronously replicate the same data to a third site with no distance limitation. So this would be if you were worried about losing a particular country, for example. Let's say that you have got your two sites for MetroCluster are in Singapore, and you're worried that the whole of Singapore is going to go down for some reason. Well, for that, you could also replicate using SnapMirror outside of Singapore. The data can also be backed up offsite with no distance limitation with SnapVault. So you can have offsite with no distance limitation for both DR with SnapMirror and also for backup with SnapVault. Okay, that's everything to tell you about MetroCluster. I don't have a lab demo for this because it's not supported in the simulator, but to be honest, this is not something that you're going to be configuring on a day-to-day basis anyway. With MetroCluster, it is set up just one time. Once it's set up, that is it done. And when you are using MetroCluster, normally you're going to be getting it from the factory like that anyway. So it's not something that you're going to have to configure, but it is something that you need to understand if you're using it, and also understand how it's working and how to fail over and how the failback works. Thanks for watching. If you want to get hands-on practice with NetApp storage for free on your laptop, then you can download my free ebook, which you can see above my head right now. Also check out my NetApp Storage Complete course, which will teach you everything you could possibly want to know about ONTAP. Thanks.